When we analyze a member in our structure, we want to know what is the area. As you remember, stress is force over area. But we also want to know what shape is the thing. Where is the material and how is it distributed? In this section of our book, he's got this incomprehensible sentence here. Force in structural design has little significance until something is known about the resisting material, cross-sectional properties, and size of the element resisting the force. Let's go tear that apart. So he's saying force is great. That tells you how much the external force is, but you still need to know how big is the area, and you need to know the stiffness of the material, and you know about that. That's modulus of elasticity. And you need to know the cross-sectional properties. That's moment of inertia, the stiffness of a shape. So moment of inertia is a property that combines what shape the thing is and how big its area is. And it's all about resisting bending. It's all about stiffness of a shape. How much material is there and how far is it away from the bending axis? So to illustrate moment of inertia, you could get yourself a piece of paper, like out of a printer or something. And if you just hold that piece of paper, it's not stiff at all and it just flops over, right? But now, if you just change the shape of that piece of material and curl it like in this picture, you have the same area, but you have moved part of that area far away from the bending axis, and now it's so stiff you could actually carry a pencil on it. Or you could take that same piece of paper and fan fold it and put it on top of a couple of supports, and it would be stiff enough you could support a book on it. What you have done is you've taken the same area and increased its moment of inertia. You could take a popsicle stick, one of those wooden, or a tongue depressor. If you just lie it flat over a couple of erasers, it's pretty flexible. You could push down on it. If you take that same stick and turn it up on edge, you have now moved the material out away from the bending axis, and now it's pretty stiff when you try to push down on it. You haven't made it any greater in area, but you've changed the moment of inertia. Or you could take a 2x6, maybe go out in the yard and put this 2x6 across a couple of concrete blocks. And if you have somebody try to walk on that or put a weight on it, it's pretty flexible. But take that same 2x6 and roll it 90 degrees, put it up on edge, and it's so stiff that somebody could use that as a balance beam and walk across it. And what you have done is you have moved the area out farther away from the bending axis. Here's our book illustrating that. He's taken a rectangle made out of cardboard or sheet metal or something, and he cut out chunks of area, squares, and moved them out away from the axis and glued them on to the outside here. He has essentially taken that one piece of stuff and turned it into a wide flange shape. And so it now is more stiff because it has material out away from the axis. Here he is again illustrating two different shapes. Oh, they might be made out of sheet metal, let's say, or steel plate. These two shapes have the same area, same number of square inches, but the one on the left is a wide flange, and I bet you can guess which one will be harder to spin. The one on the left, because it has moved its material out away from that axis, it is harder to spin. In other words, it resists bending. And that's what moment of inertia is all about. It's stiffness of a shape. How does the material resist bending? And we're interested in that when we're putting beams in our buildings and bridges. I'm going to take a little detour here and you may or may not want to zone out, but I want to tell you why we call it second moment of the area and why we use the units we do. So hang on. Last week we looked at how to find centroids, and you'll remember that we used moment equals area times distance. We found the moment of the area in order to locate our centroid. When you find moment of inertia, you take that moment of the area and you multiply it times distance again, distance squared again, and so you actually get area times distance times distance. It's called the second moment of the area in some books. We're not going to call it that, but that's what it is. It's the second moment of the area. And if you got more involved in the math of these things, you'd be glad that you knew that. So we're just about done with the centroid thing. I just wanted to think about what units is moment of inertia expressed in. If moment of inertia is the second moment of the area, if it's area times distance squared, well, area is square inches, and distance squared is another set of square inches. Inches squared times inches squared gives you what? Inches to the fourth. So moment of inertia is another name for second moment of the area, and its units are expressed in inches to the fourth. Not that you would ever have a measuring tool that would measure inches to the fourth, but mathematically that's what it is, and when we look it up in tables, that's what we find. Speaking of looking it up in tables, if you wanted to know the moment of inertia of a shape that you were working with, you wanted to know how stiff was that shape, you could look it up in tables, and we have one in our book. There are special shape tables for structural steel. AISC has given us those tables for all the steel shapes. If you're sticking a bunch of shapes together, you can calculate your own moment of inertia, and there's a section in our book where he shows us how to do that, but we are not going there. So here's the section in the book where he shows you, here is the moment of inertia for a rectangle. And this is just the formula. Base times height cubed divided by 12, that's its moment of inertia. Here are some other moments of inertia, if you need them. Here is the table out of the steel manual, also out of the back of our book. And notice that there are two columns that say moment of inertia. See that, inches to the fourth? One around the x-axis, if you have your beam standing in normal orientation, and one around the y-axis if you're bending the end of your beam side to side. Well, we think about moment of inertia when we're looking at columns, and here's our sheet of paper again. If you try to press down on that sheet of paper, that is about worthless. It's just too floppy. But if you roll it like you did when you were carrying a pencil, suddenly you've increased the moment of inertia, it becomes stiffer, and you can put a weight on top of it. You could take, let's say, that piece of paper, fold it, and the folds by themselves increase the moment of inertia, and then glue them together to make a paper wide flange shape. You've got a pretty stiff shape there compared to that floppy piece of paper. And the more the material is spread out away from the axis, the stronger that column is. So you could take that piece of paper and fold it several times and glue the edges together, make kind of a square column. That will be a real stiff shape, even though it's made out of thin paper. It turns out that the stiffest shape is circular, so the shape of a tube or a pipe. That gets all the material out away from the axis as far as possible. Now with beams, Usually we are loading a beam from this direction, aren't we? We're bringing down the load from above, and so we will usually use a wide flange because that pound for pound, pounds of steel, that will optimize the stiffness in the direction where we need stiffness. It will get flange material out away from the bending axis. With columns, though, we don't know what direction the load is coming from. It could come from any direction as the wind blows and the forklift runs into it and there's an earthquake and one thing and another. So a cylindrical tube is the best shape for a column. However, a circular tube is not very easy to weld angle clips to, so what you usually see in a column is a square shape or a rectangular shape or sometimes a wide flange shape. If you're out there in the world seeing dump trucks go by, think about how the side of the truck is made. This is one continuous piece of plate. I don't know what it is. It might be 3/8 plate, but it's a big old flat plate. But what did they do? They put it in a press brake and they bent it, they formed it, and they made those ribs in there. There's one example. Here's a different example. Here's one that's been formed with some curvy stuff in it. They took that one piece of plate, similar to your piece of paper, and they increased the moment of inertia by moving part of the area out away from the axis. Well, you find the same thing happening in corrugated cardboard or corrugated roofing or that foil material with honeycombs inside. Those are all strong because they have a high moment of inertia. How? They have moved material out away from the axis. It's as simple as that. Here's a nice illustration. This is a moth. This moth was dead when someone found it. That someone happened to be a person who worked at the Centers for Disease Control. And they were out there on their lunch break and they saw the moth on the sidewalk and they said to themselves, "Ha, I've got an electron microscope. I think I will look at this moth wing." And so here they are gradually magnifying the scales on that moth wing at higher and higher magnification until here at a little over 22,000 times magnification, look what you've got. High moment of inertia with stiff ribs moved out away from the bending axis in 3 directions and then lightning holes to keep it lightweight. Perfect design. So beams, we've been talking about the bending axis, and the axis goes through the centroid, through the middle of the beam. And the material out away from that axis is what does the work. So as you remember from trusses, at the top of the beam it's in compression, at the bottom of the beam it's in tension, and it's those flanges that do the work of making our beam stiff. The deeper the beam section is, the greater the moment of inertia because you've got material moved out away from the center. So let's look at this last slide. Here is an excerpt out of our old friend, the structural steel wide flange tables. And I've zoomed in here on the moment of inertia around the x-axis. So here is the x-x axis, the bending axis. And look here. An 8x10 wide flange has a moment of inertia of 30.8. There's its picture. An 8x67, there's its picture, has a moment of inertia of 272 inches to the 4th. Look at that huge difference. And how did they do that? They moved a lot of steel out to the far flanges, out far away from the axis. And this now has stiffness of a shape, ability to resist bending.